And this is a project about detecting fraudulent transactions using AI. First, we'd like to talk about the background of the rising issue of financial fraud. First, we see that 51% of organizations have experienced fraud in the past 2 years, which is followed up by a 70% increase in the amount of credit card fraud since 2019. This is mainly due to the COVID-19 pandemic. And finally, from the Bureau of Customer Protection, it is reported that 65% of people will experience credit card fraud in their lifetimes. Therefore, we assess that early automated detection is imperative to combat credit card fraud. Our goal is to create a model that will take in all transaction data and process it and assess what transactions are likely to be fraudulent and alert the bank and credit card holders very early on to prevent any long-term damage that could result from the credit card fraud. Users that we assess would be interested in our model would be account holders. This would allow them to minimize financial losses, protect their credit card scores, and protect their personal information. Secondly, banks and stakeholders will be very interested in this model. One, it'll help them improve their ability to follow government regulation. It'll decrease the likelihood of them having a lawsuit or paying out a lot of money to customers who have experienced a breach in their security. At a higher level, it will maintain a healthier economy by limiting the amount of theft and financial crime that can go on. And finally, it will protect clients from direct and indirect consequences of fraud, helping their bottom line and their customer satisfaction. Next, we'd like to talk about the data that we used for our project. We had to use simulated financial data, mainly for privacy reasons. Unfortunately, banks do not lend out their customer information readily, just on a whim. But on the upside, we did get access to over 6 million transactions, and they're simulated over a 31-day period, so the data is very rich. The data we did have access to clearly outlines which transactions are fraudulent and which transactions are not fraudulent. Now we'd like to talk about the main inputs and the feature engineering we did for the project. First, we looked at the number of transactions that are fraudulent versus the number of transactions are not fraudulent. And we see that the overwhelming majority of transactions have no fraud involved. This gave us some issues considering how sparse our data is, but it is reflective on how actual financial data looks like in the real world. We then looked into the differences between client-to-client and client-to-merchant transactions, and we found that no client-to-merchant transactions have fraud based on an assumption in the simulation model. Similarly, we found that only cash out and transfer transactions contained fraudulent transactions. We were able to incorporate this as well as the type of transaction, either client-to-client or client-to-merchant, into our pre-processing to improve model accuracy. Then we looked into transaction amounts, and we found that a large change in the origin balance leads to a higher rate of fraud. Similarly, if that's coupled with a minimal change in the destination account, that is also linked with a high likelihood of fraud, seen in the blue dots in the graph below. Finally, we look at transactions over time. First, we see that the day of the month is very important in the model, since the number of fraudulent transactions is consistent throughout the month, even though we see a large decrease in total transactions in the second half of the month. Secondly, we see that the day of the week is very important in the model as well, since the number of transactions that are fraudulent increase on Tuesday, Wednesday, and Thursday, and then decrease for the weekends and on Monday. And finally, we found that the time of day a transaction occurs is important in the model as well, since transactions that happen early in the morning are more likely to be fraudulent than transactions that happen during normal business hours and later at night. We would now like to go over the model that we used to detect financial fraud. For our model, we decided to use a generative adversarial network. And the first part of this is creating a generator model. We pretty much use a unsupervised neural network that captures the probability of seeing X and Y, where the inputs are random variables, usually just uniform distributions that introduce noise into the network. And with this, we're going to learn how the data is placed throughout space. And the goal of this is going to be able to learn key insights about the data through the hidden variables that we will learn, and then eventually create new random samples mimicking the real samples by just entering random noise into the network and the weights and biases will be trained in order to mimic the real data. The second part is a discriminator model. This pretty much is a binary neural network classifier that captures the probability of seeing label y given x. The inputs are either going to be the real genuine data or the generated data from the generator. And it's going to learn decision boundaries on what real data looks like and what generated data looks like. And the goal here, I already kind of talked about this, but is assess what data is from the generator and what data is genuine. In order to train these two competing neural networks, we first start with the discriminator neural network. You can see here, we only focus on discriminator and do not change the weights for the generator. The second up is the generator network. You can see here the discriminator network is important when creating the generator model, but we only change the weights regarding the generator model and we don't change the discriminator weights. And this process will continue for many iterations, the generator competing against the discriminator and the discriminator competing against the generator until we reach convergence. Convergence is when the discriminator is wrong 50% of the time. This pretty much means it's randomly guessing on what's real data and what's false data, pretty much meaning that our generator is as good as the real data. The issues here is really hard to get to convergence to the 50% line, since the discriminator outputs are more random the closer we get to convergence, meaning backpropagation becomes useless near the end. This was the section of code we used to create the iterative pattern of the generator working against the discriminator and the discriminator working against the generator in order to get to a point of convergence. All right, to get into some more detail on how the models work, we'll first talk about the generator model. Forward propagation for this works by creating random variables that we input into the generator. These random variables are then used to create simulated data by going through several layers of biases and weights, and then the simulated data is then outputted into the discriminator model. Backpropagation is done by first calculating the generator loss penalty. This is regards to how good the simulated data was at fooling the discriminator. And the loss penalty is then brought back through the discriminator and generator networks to create pretty much the effective error that is used to calculate the gradients, which improves the generator weights in order to create simulated data that will be able to fool the discriminator. And with each iteration, the weights improve and increase the ability of the generator to turn random noise into simulated data that can fool the discriminator. And we can see in this section of code that we can use the loss function values to improve the weights of the generator model to better convert random numbers into simulated data. In the second model, the discriminator, forward propagation starts by receiving an input which is randomly assigned from the genuine data set or the generated data set. And then with that input, a binary classification is determined on if the discriminator thinks it's real or generated data. And then the backpropagation is done by starting if the classification is wrong. So if the model says it's genuine data, but it was fake data, then the discriminator loss penalty is determined. This effective error is calculated. The gradients are then assessed based off the effective error at each node, and the weights are improved for all weights in the discriminator. As you'll see in this section of code, as I was saying, if the discriminator model is wrong, we will improve the weights in such that you'll be able to detect what data is generated and what data is genuine in the next iteration. But else, as you can see in the bottom one, if it is correct, we don't change the weights too much since the model is already guessing which data is right and which data is not right. The loss penalty I was talking about, we'll dive into some more detail about that, and at a high mathematical level, the goal is to reflect the distances between the distributions of generated data and the distributions of real data. The method we use here is a minimax. Pretty much the goal is for the generator to minimize the losses and then just trying to maximize the losses. In other words, the generator wants to fool the discriminator, and the discriminator wants to catch the generator. The equation here, I won't go dive into too much of the details, but pretty much we want to minimize the maximum likelihood that the discriminator can catch all the real and all the generated data. And although this section of code looks very simple, but when it is used in conjunction with the other sections, it is very effective at penalizing the discriminator and the generator function in order to improve their performance with several thousand iterations. Then after training, we will store the discriminator model, and we'll use that to predict if a transaction comes from the fraudulent data set. The model outputs, this is at a high level how the model will work, which each transaction from the bank will be put into the model. The inputs we'll formalize from earlier are going to be the hour, the day of the week, the transaction type, and the destination and source account balance change. And once all that is calculated, the model will predict a probability if the transaction could have been generated from a fraudulent data source or if it was from the non-fraudulent data source using the discriminator. Now we're going to talk about how well the model performed. First, we'll look at the loss functions for the discriminator and generator functions. As we can see, with more iterations, both of the losses decrease, and it is likely that generated data is able to fool the detector. This is further proved by the data generation, as we can see that the spread of the actual data and the simulated data are both very similar, indicating that the generator is very robust at creating generated data. When it came down to how well the model performed on detecting fraudulent data, it was okay. About 7% recall rate, which indicates that the majority of fraudulent transactions will be detected by the model. However, this does allow for a sizable minority of transactions to go undetected, which may be unacceptable to some banks. Moreover, we see that even with adding additional generated data, the fraud detection rate does not improve by much. Is very negligible at all. Even when we get towards like the 5,000th iteration of the GANs model, it's still around a 7% recall rate. And this is juxtaposed to the point if we add actual fraud data that we know is fraudulent, the model should be performing a lot better when we do add more data. So that's another weakness of our GANs model. In our final section, we'll talk about some of our reflections and our conclusions and final thoughts. First, usability. Overall, the model cannot be used to detect financial fraud. It struggled to classify what transactions were fraudulent enough with enough consistency to be used in the real world. And another issue is that training is slow, which limits how much banks could use this in real time and how fast the model could learn new fraudulent transaction types. But the best uses for the model, one, it can track trends and detect new patterns in all transactions because at its heart, it's really an unsupervised method. And it can assess if there's a sudden change in the level or method of fraudulent transactions. Some conclusions based off a key question we had: could we use GANs, which is usually an image processing technique, on non-image processing methods? We were interested in this because it's a very powerful technique used in a lot of AI, visual AI techniques. Unfortunately, the model did struggle to identify key differentiating variables. Some of the issues I ran into is that we underestimated the ability of the model to reach convergence on non-image data and some of the difficulties in turning this into a non-image question. And finally, some future improvements for our project, if we ever come back to it. We could first implement a more supervised technique, since the generator model did learn a lot about the data, and we used some of the insights learned from the hidden variables. And secondly, we could use a more human-centric model, since GANs and other deep learning methods are very, very powerful, but they have very low explainability. This would be beneficial since a lot of analysts and people like that do not find a black box solution always the most useful. And finally, we'll talk about the team collaboration part of the project, and we'll go over the division of work. But even though we decided that all three of us worked evenly on the project, even though we divided up amongst ourselves by focusing mainly on like the EDA and the PowerPoints, we also divided up by just focusing solely on creating the GANs model, like developing the code for the discriminator and the generator model, and then creating the code that would make these two models work against each other in order to create the fake data, and then analyzing that data to detect fraud. But thank you for listening to our presentation, and have a good one.